Hey there, Calc 2 folks. Back here, moving on in our studies, heading towards the end of the semester here, where we do have to finish with here the getting into introducing ourselves to vectors, the fundamentals of vectors, the idea of a vector, the operations we can perform with vectors, the properties of those operations, the notation involved, uh, and then some uses for um, all of this presented here in the next few lectures, right? Next few of these video lectures here, where we are going to start with introducing the idea of what it is to be a vector in 2 and 3 dimensions. What we take note of is that, first of all, calculus involves both the study of scalar valued quantities, right? As we've been really studying up to this point, right? We've all the quantities we have really considered have been what we might think of as being scalar valued quantities. The functions we have encountered have been scalar valued functions. The numbers we have calculated have been scalar valued numbers, right? But calculus also involves quantities known as vector value quantities, right? Or simply just the idea of a vector, right? And what vectors are a numerical value, just like any other real number that you might understand along the number line as being a numerical value. A vector is also thought of as a numerical value, right? But it's a numerical value that goes a little further than what we understand as a scalar value. All right? What do I mean by all that? Well, let me bring my definition up here into view. All right? Here I define both a scalar valued number and a vector valued number and highlight a little bit on notation, right? A scalar valued number is just a number indicating magnitude, size, or scale in its value, right? It's just a number that represents magnitude, size, or scale, right? It lacks what we include in the idea of a vector, and that is what we think of as being some sort of direction associated with the value. Vector valued functions, right, are numbers that indicate both a magnitude, size, and scalar like a scalar valued number would, right? But along with that description of size, indicates a direction that occurs within an n-dimensional space. Right? And we're going to consider the cases for 2 and 3 dimensional space. Now, in general, a scalar value may be represented by just a variable using notation like u, or like a little u or a little v, or often the most common is the value little x, for instance, right? Where that value would just represent or illustrate a scalar value in its notation. Whereas if we want to consider what we think of as being a vector value in its notation, that is illustrated as you will see me do here, both on the board and in my notes, as I use this vector notation seen here, where it looks a lot like a scalar value we see, but I incorporate this arrow right above that scalar value. That arrow above that scalar value, that bar, is indicating that this value is actually a vector value. It's a value that highlights both a scale, a magnitude or size, and a direction associated with this value. All right? Now, in the text doesn't typically put the arrow. What the text will do is they will use a boldface. Right? They will use a boldface font. You might see something like a bold V instead of an unbolded V, or you might see a bolded V with that vector notation on top, depending on what text you are referencing, right? But these are common ways that we illustrate this vector value, this value that represents both a size and a direction, a magnitude and a direction. And there's a lot of instances where we consider describing values with vectors, right? A lot of places in the sciences. For instance, the pull of gravity, right? The pull of gravity at any location in space has a certain magnitude to it, as well as a particular direction that it pulls in, right? A impact force on an object, right? That force has a particular magnitude and a particular direction when we move out into n-dimensional space, right? These are instances where we might consider using vector-valued functions or vector values in their descriptions, and vector-valued functions to describe these scenarios in a more general context, right? But again, in the world around us, there are a lot of examples that involve describing a variable using not just a scale, a size, or a magnitude, but also giving that scale or size or magnitude for that variable a direction that scale or size or magnitude is occurring in. All right? Now, we will take some note on some notation here. I do continue my notation. All right? We have what's called component notation. This is one of the first notations that we are introduced to in our study of a vector, right? And in component notation, if we were, for instance, in two-dimensional space, where how do we understand two dimensions? It is the crossing of two one-dimensional systems, two number lines, are going to be crossed with one another, right? And that is going to perform form what we call two-dimensional space, right? And a vector denoted within this space, right, may be expressed using what we call component notation with this notation seen here, right? This is known as component notation, highlighting what we think of as being this vector we call vector v, right? This component notation does place what are two scalar valued quantities between these things that look like greater than and less than or equal to, or greater than or less than symbols. Those are actually vector symbology used here in my notes, right? That it will be common in a lot of text, right? And I do think is common in our text, right? And the values of v1 and v2 are what we call scalar valued components of that vector. This first component is referred to as, if we're talking about two-dimensional space being described by variables x and y, this first component would be called our x component, and the second component might be referred to as our y component. And what they are representing there is the idea of displacement. They are describing a distance and a direction traveled from one location in our dimensions of R2 space to another location in dimensions, in our R2 space, right? They do represent displacement that happens in the x direction and the y direction if our R2 space is described in terms of x and y, right? If we were to move to 3 dimensions in our notation, right, we would essentially be crossing two-dimensional space with a third real number line. And if we cross 2 dimensions with another real number space, that will present a 3-dimensional number system, right? Where these 3 number lines all come together at right angles to one another, forming our description of space that describes space by being able to move forwards, backwards, left, right, and now up and down. This third description of R highlighting that third direction, right? If R2 is often described using the variables x and y, we should understand that this third dimension of space is commonly described using the variable z. We might say we have an x, y, z coordinate in our 3-dimensional space, right? And similarly, we can have an x, y, z vector in that space, and a vector existing in this 3-dimensional space denoted in component form would take on this notation here, where in component form that vector will now involve 3 components, where if we think about our space being defined by x, y, and z, right? The first component will be what we call the x component. The second component might be what we call the y component, and the third component might be referred to as the z component, where again those components are just scalar values representing displacement, right, within the three respective dimensions of our three-dimensional space, right? They represent displacement in the x direction for the first component, the y direction for the second, and the z direction for the third. That direction, or that displacement, being a change in position that is also summarized with direction. You can move forward on the number line, or you can move backwards on the number line, a value of little v, right, for the scalar value of little v, described by each one of these components, right? Let's take that a little further. Right. At any location in R2, R3, a vector v can be illustrated actually also as an arrow, where scalar values are often thought of as being like points on a number line, right? In 2 and 3-dimensional space, vectors, or these vector valued functions, are actually what we might think of as being arrows within that space, or can be illustrated by an arrow in the space, where the arrow has a certain direction that it points in, and that is the direction represented by the vector valued function, and that arrow in that space has a certain length to it. The length from the tail, where it originates, to the point that it's pointing to in terms of its displacement, its summary of displacement, which is called the head of that arrow, right? And the distance from the tail to the head is what we call the length of that arrow, right? Indicating what we know as the magnitude, or the size, or the scale of that vector value, right? As vectors have both a direction and a scale, the arrow highlights both of those values in its illustration. All right. Well, let's see what I follow this with. Oh, we do take note that if an arrow is presented in n-dimensional space, right, or if I really should say if the arrow represents position itself in okay, let me pause this for a moment here and make sure I have this idea correct. All right, I'm back. I think I have this fixed with how I want to say this. A vector v is said to be in standard position, right, in either what we think of as being 2 or 3-dimensional space, if the arrow representing position in 2 and 3 dimensions has its tail at the origin in the system, right? In standard position, our vector v indicates both the direction and the magnitude from the origin of R sub n, right? In R sub n, let's say it this way, the standard position of vector v indicates a direction and magnitude from the origin of R sub n, right? I want to be a little specific there because, again, we're talking dimensions of space, and an arrow is an item that exists in 2 and 3, and you could even say perhaps one dimension of space, being that you can move left or right. But when you move up into 4-dimensional space, or go beyond the 3rd dimension, to say that you have an arrow in that space just doesn't sound right. So I wanted to make sure I clean that up. But I also want to be clear that you can be thinking of a vector n-dimensionally, and it can be thought of as being in a standard position in that n-dimensional space, right? So I think I have made that a little clearer, hopefully, with this definition. All right. Now, if we do consider the case for an arrow that we can visualize, or a vector that we might be able to illustrate, and illustrate with some ease, let's consider 2-dimensional space, right? For example, consider the vector v equal to v1 comma v2 in standard position, right? In general, this 2-dimensional vector in standard position illustrates an arrow in 2-dimensional space with the tail at the origin of the system and the head located at the xy coordinate v1 comma v2. And if we note the illustration of what would be the representation of this vector in standard position, that representation might look like this in 2 dimensions. Here we are in our 2-dimensional xy plane, and here we have this arrow illustrated in standard position. The tail of the arrow is located here at the origin. The head of the arrow is located here at this coordinate v1 comma v2 with respect to x and y, where what this arrow is representing is this vector we call v1 comma v2. All right, I do have a little difficulty putting in vector notation and bold notation, so I do clearly denote this vector with its component notation in this illustration. Take note. All right, so just to denote this generic illustration of vector v. Right? This is what we mean by a vector in 2-dimensional space. It is this quantity that points in a certain direction in 2-dimensional space and has a certain size or scale or magnitude to that quantity, where direction is highlighted by the direction of the arrow and that size or scale is measured by the length of that arrow. All right? And what a vector in standard position describes is a displacement that happens from the origin in the system. Right? We might have this displacement for an object, right, in our system that starts at the origin. Well, that would put that object at this location if that displacement is described in standard position. All right? If we were to consider the magnitude of this vector, right, what would be the length of this vector we see here? That's given by just a little Pythagorean theorem. What you will notice is that vector does form a right triangle in this space. The base measurement of this right triangle might be v1. The height of this right triangle might be v2, right, what we measure along the y-axis. So the distance along that arrow, right, the length of that arrow would be the hypotenuse of this right triangle, and it would be given by the square root of v1 squared plus v2 squared. It is given by this measurement here. And keep in mind, magnitude or distance is always going to be measured as a positive value. It's always going to come out as this positive description, which is what this formulation will present. Right? Squaring the two values of v1 and v2 will turn those positive. When summed, you will then have a positive result. When you take the square root of that, it will thus then be positive, or at least greater than or equal to 0. There is the one case of the 0 vector, which is a vector, right, that points in no particular direction and has 0 length. It's indicated by a vector whose components are all 0. In that case, you will get a magnitude of 0, but it is the only case of a vector that would yield a non-positive or a non-negative magnitude is how we want to say that. Now, we can't formally define this, right? We do, right? For the vector v in R sub n, the magnitude of v is denoted, first of all, using this notation here, right? What you will often see in my notation when I denote the magnitude of a vector is I do denote it with a double absolute value symbol wrapping around that vector. All right? What you will see other authors do and other mathematicians do, they will sometimes just simplify that to a single absolute value symbol. Right? And that's some of what you need to keep in mind is absolute value does mean distance from the origin. Right? So when we do see this idea of looking at a vector's magnitude, we are looking at a vector's what we would think of as being its absolute value. I just was classically taught that that magnitude is highlighted by double absolute value symbols because we are talking a vector value, whereas and it makes it a little clearer in identifying that, whereas this single absolute value symbol is used in the illustration of a magnitude of a scalar value. All right, sorry folks, I'm back here. Again, in terms of the magnitude, it does have its notation, right? And then if we consider the couple of cases that we're going to be considering magnitude in its calculation, that would be 2 and 3 dimensional space, where in the case of a component vector here presented in 2 dimensions, right? As we had noted above, the magnitude is just the, again, square root for the sum of the components squared. And the same thing is seen in the case for the vector presented in 3 dimensions. It is just the square root for the sum of the components squared. You do take the square root for each of these components squared and then summed together. Right? So that is our magnitude calculation in both 2 and 3 dimensional space. If we consider a quick example here, right? We might consider the vector described by v bar equal to -3, 6, 1. Right? If we were to plot this vector in standard position and look at its length, or actually we could plot this at any position and look at its length, this vector would say that it has a length of the square root of 46, and that is just coming from the square root of the square of -3 is 9, the square of 36, or sorry, the square of 6 is 36, so 9 plus 36 is 45, and the square of 1 is 1, so 45 plus 1 is 46 underneath that radical symbol. Now, does that simplify? I do not think so. I don't think that simplifies or breaks down into any sort of prime factorization. So square root of 46 is a good deal there, right? For magnitude, folks, of that vector. And that is just this calculation seen above. Now, where do I go from here? Oh, as with scalar values, fundamental mathematical operations can also be performed with vector values. Right? What we're going to look at now is the beginning of some vector operations. Right? And a couple of the fundamental vector operations we have are the case for vector addition, subtraction, and what we call scalar multiplication. For these 3 operations, we have them defined as follows. Again, it's what you might expect, right? If you have 2 vectors, u and v, right, in n-dimensional space, and we let c be just a constant in a sense of the scalar value constant, right, the scalar constant value, we might say. Right? The sum of vectors u and v is just going to be given by vector u plus vector v. The difference of vector u and vector v might be presented as vector u minus vector v, and the scalar multiple of the scalar value c with some vector v is given by c times v, where here we are a little cautious with our product symbols here with vectors, as we're going to see there's going to be what's known as a dot product and a cross product that develop in the next couple of sections, where we want to try to avoid confusing these calculations with the scalar multiplication with the cases for dot and cross product. So here, do just highlight we're presenting multiplication here just by setting the 2 values next to each other. That constant value c placed next to a vector v is highlighting scalar multiplication of c with v. In terms of their calculations, right? We might note in R2, right, if u is equal to the vector u1 comma u2 and v is equal to the vector v1 comma v2, well, u plus v is just u1 u2 plus v1 v2, where we have a rather, what you might think of as a rather intuitive process here, where all we're going to do is add up, in the case for addition of 2 vectors, add up the components for each of the vector. The First component in the sum will be the sum of the first components in each of its terms, right? The vectors found in the two terms of that summation. And the second component in our sum will be the sum of the second components found in the two terms of this vector summation. Similar results are seen for the difference of two vectors. U minus V does mean U1 comma U2 minus V1 comma V2, where we are going to find the components in that difference formed by taking U1 minus V1 for the first component and U2 minus V2 for the second component. And lastly, if C is a scalar multiple, the scalar multiple of C with V would be given rather intuitively as just the value of C times the vector v1 comma v2, where what you will see happen with C is that it distributes itself in a product to those scalar values inside the components of vector v. Right? It will distribute itself to those scalar values there. Right? And what we can note is you do see similar results for the cases of U and V in three-dimensional space, and this is all true even up and through the nth dimension in terms of their calculations. So let's just consider a quick example here. And let's consider it in three dimensions, since we aren't going to necessarily present the formula for those, but we will see that it is very similar, right? If we were to present ourselves with vector u being the vector 4, -1, -8, and vector v to be the vector -3, 5, -5, and c be the scalar constant value of 10, well, if I was just to take u plus v, that would be vector u added to vector v, where if I go through the components of u, right, the first component of u is 4, the first component of v is -3, add those together, I get +1. Add together the second component of u, that's -1, with the second component of v5, you do get the constant value of 4. And if we do that similarly with -8 and -5, the third components of vectors u and v respectively, add -8 to -5, you will get -13, the third component in the summation. Right? Their differences, presenting u first, followed by taking away from that vector v, is what's going to give us the difference of these two vectors, right? U minus v. 4 minus -3 is 4 plus 3 or 7. -1 minus 5, well, that's -6. And -8 minus -5, well, that is -8 plus 5. That is -3 in value. All right, so u minus v in this case results in the three-dimensional vector 7, -6, -3. If we were then to consider that scalar multiple of 10 times vector v, v being the vector -3, 5, -5, well, that 10 will just distribute itself to each of these terms. 10 times -3 is -30, 10 times 5 is 50, 10 times -5 is -50. Right? As you can see, these rather fundamental operations in vectors or well, I should say these operations with vectors, addition, subtraction, and scalar multiplication, happen rather intuitively and are rather, like I said, fundamental in their behavior and really what you might quite expect to be their behavior. Right? We do point out some usefulness to this idea. Vector addition and subtraction, right, can actually be used to describe vector location that is not in standard position. Right? We might suppose that vector v1 comma v2 is located at the coordinate a comma b in R2, right? Meaning that its tail is positioned at the coordinate a comma b in two-dimensional space. Well, the location illustrated by vector v then will be given by vector u in standard position, where u would come from taking the corresponding vector pointing to that location at AB, that vector a comma b in standard position, and adding that to v1 comma v2. right? Adding that to vector v. If you take the vector pointing to this location, right, or form the vector that points to this location in standard position, and you add it to vector v1 comma v2, you will get vector u, the standard position description of where v points at in its space. What would be, in a sense, the sum of these two vectors. Right? Now, if you knew the location of u and you happen to know where v, or what v resembled, right, in terms of its two-dimensional vector, you could find its location in space, v's location, at a comma b using a little vector subtraction, right? Whereas if vector v indicates the location at the coordinate a comma b in R2, hold on here, let me double check, make sure I have this right. Okay, I do have this correct. Here we note if vector v indicates this location in space, meaning its head points at the location a comma b, the position of vector v in that space is described by the location in R2, illustrated by vector u, which is in standard position, right? By position of vector v, we mean the tail's location, where the vector happens to be emanating from in the sense. Where we can find that location using v's description and using the location where we know it indicates where it's pointing at, a comma b, can be found by forming this difference. All right? It is the vector formed with that location a comma b minus vector v. Right? That will tell us u, right? Where u is describing the tail's location in vector v in this calculation. All right? Sum and differences of vectors is used to help orientate a vector's location in space. Right? If we know a vector and we know a bit of specifics about its location, either where it begins from or where it points to, we can determine those locations where it points to or where it begins from by using a little vector addition or subtraction with the known vector and the known bit of location information. All right, in one of these two formulations. All right. As for the scalar multiple of a vector, it can be used to define parallel vectors, we say, right? Vectors u and v are parallel vectors if for the scalar value c, u, vector u, can be written as some constant multiple of vector v. Or likewise, vector v could be considered to be written as some constant multiple of u. If two vectors can be written as constant multiples of each other, they are what we call parallel to one another. Right? And along with that, the scalar multiple of vector can also be used to define what is known as the unit vector for a corresponding vector. Right? For the unit vector v bar in R sub n, right? The unit vector corresponding to v bar, right, is just going to be a vector parallel to v, right? Meaning that it's pointing in the exact same direction as v, but it has a magnitude that is only 1 unit in length. That is what it means to be a unit vector for a corresponding vector, right? It's a vector that's parallel to this, meaning it's a constant multiple of this other vector, right? But it's also, meaning it points in the exact same direction as this other vector, the vector that it is a unit vector representing, right? But it only measures 1 unit in length. It's a way of summarizing, in a sense, direction without considering magnitude for a vector, all right? If we look at a calculation of a unit vector, right, we might consider finding the unit vector for this vector here, v bar equal to 3 comma negative 2 comma 5. Well, in the unit vector calculation for v here, we are going to need to divide v by its magnitude. That is what gives us the unit vector for a corresponding vector. Is if you take a vector and you divide out its magnitude, you will have a description of a unit vector for that vector. And here in vector v, the magnitude is just given by the square root for the sum of each component squared, right? Where 3 squared is 9, negative 2 squared is 4, and 5 squared is 25. That is 9 plus 4 is 13, plus 25 makes 38 in value underneath this radical symbol. All right? And there's no prime factorization for the square root of 38, so we'll leave it as the square root of 38. And we end up dividing then v by that value given by 1 over the square root of 38, or just the value, well, we divide by the square root of 38 or multiply by that constant multiple 1 over the square root of 38. And what happens is this 1 over the square root of 38 distributes itself through the terms of this vector, the components of this vector, term by term. It behaves according to a distribution property. And we're left with 3 over the square root of 38, comma, negative 2 over the square root of 38, comma, 5 over the square root of 38 here. Where what we are highlighting here, folks, is this is a vector that is parallel to this vector. We can see that because it is a constant multiple of that vector. It is 1 over the square root of 38 times that vector v. Right? It has that parallel property. But what's also unique about it is if I spent the moment calculating the magnitude of this vector here, squaring each of these components and adding that up, I would have the square root of 38 over 38, which is the square root of 1, which equals the value of 1 in the end. And I would have a magnitude of this unit vector measuring 1 unit in length. What this vector does is it points in the exact same direction as v, right? Meaning that it's parallel to v, but it's only measuring 1 unit with its magnitude. All right? That is what we call a unit vector, and that is how they are calculated. And that does come from a little scalar multiplication and this understanding of being a parallel vector. Lastly, we note here, scalar multiplication and the concept of a unit vector can be used to also denote vectors using what is called standard unit vector notation. All right? In addition to using component form to denote a vector, we can also denote a vector using what we call standard unit vector notation, which is what we're highlighting here in this definition. All right? For instance, we might have the vector v here in two-dimensional space. If v is equal to the vector v1 comma v2 in two-dimensional space, it can be expressed in what we call standard unit vector notation as v bar equal to v1 times I bar plus v2 times j bar. Or what I bar and j bar are known as is these are known as standard unit vectors. All right? I described them down below here, along with what we'll see added to that as a standard unit vector in three-dimensional space. But these are, respectively, indicating the direction of the positive values for each dimension of these spaces. In two-dimensional space, right, I bar is just the unit vector 1 comma 0, which points strictly along the positive x-axis 1 unit in length. And vector j bar is the vector 0 comma 1, which is also strictly a unit vector that points in just the positive y-axis and is 1 unit in length. Right? When we take those vectors I bar and j bar, sorry about that again, the garbage just got picked up out front, so it was a little loud. So let me jump back in here. If vector v bar, right, equals v1 comma v2, and you take v1 times I bar and add that to v2 times j bar, these two what we call standard unit vectors down here that occur in two-dimensional space. The scalar product of v1 with I bar added to the scalar product of v2 with j bar will result in this vector v1 comma v2, right? It will actually produce that vector description. Similarly, if we have v bar equal to v1 comma v2 comma v3 in three-dimensional space, it can also be expressed in standard unit vector notation as v1 times I bar plus v2 times j bar plus v3 times k bar. Where in three-dimensional space, again, I bar, j bar, and k bar are these standard unit vectors, these vectors that measure 1 unit in length and point in the positive direction of each of our coordinate axes defining that space. This points in the positive x-axis direction, this points in the positive y-axis direction, and this points in the positive z-axis direction of three-dimensional space. And if we take these scalar components of vector v and we multiply them by those standard unit vectors and then add up those scalar multiples, that will result in vector v forming. All right? If we look at that as an example here, we might consider the vector v equal to 7 comma 1 comma negative 2. The vector 7 comma 1 comma negative 2 expressed in standard unit vector notation could also be expressed this way as the vector 7i plus j, or 7i bar plus j bar minus 2k bar, right? Where vectors I, j, and k are the standard unit vectors 1 comma 0, 0, 0, 1, 0, and 0, 0, 1 respectively, right? Were these standard unit vectors as described in the definition, right? These are just two different ways we could consider expressing this one vector v bar. And what you will notice is if I, j, and k represent these standard unit vectors, and I was to arrange this into a scalar multiple of 7 times I bar, plus what you'll notice is this is 1 times j bar minus 2 times k bar, and I perform those scalar multiplications and then add up those results, the result is the component form 7 comma 1 comma negative 2, that vector description of v bar in that component form. All right, folks, this is the end of this first section of notes here, just kind of introducing you to this concept of vectors. This does cover, I think, our first two sections into this chapter. What I like to do is I like to combine our understanding of vectors in two and three-dimensional space into just one introduction of vectors in general. So what you'll notice here is I did kind of combine those ideas here into looking at just vectors in 2 and 3 dimensions in general, right? We want to be familiar with how they are different than what we're familiar with as scalar values, right? We want to know how we denote them, either in this component form or in that standard unit vector notation that we ended with, right? We want to know how to kind of illustrate them when we're looking at them specifically in space, how they kind of plot themselves out in space, right? We want to know how to calculate their lengths. That's all the magnitude calculation. And we want to know how to perform some fundamental operations with these vectors, right? And to begin to see how some of these fundamental operations can be used in finding things like position and describing parallel behavior and unit vectors, right? What we are going to do is add to this understanding. We're going to go a little further with our introduction to vectors, and we're going to start to look at some vector operations that are specific to vectors, right? That we kind of saw back in our scalar operations, but now is going to be extended into the realm of vectors. And that is what we call dot products and cross products, right? They both have that understanding of being a product, and if we were in the looking at scalar values, and I talked about a dot product or a cross product, the result would be what we would understand as a product, right? 2 times 3 is 6, whether I take it as 2.3 or 2 cross 3, right, in terms of a product, or I can even just set that side by side, right, in a grouping set of parentheses for the 2 and the 3. But what we're going to see is if we move now to the realm of vectors, and I have vector u times vector v, that product of u and v can happen a couple of different ways. U times v can happen as a dot product, and u times v can happen in the form of what we call a cross product. So what we're going to develop in the next 2 sections of notes are these vector products, the dot product and the cross product, and look a little at how they're used in the realm of vectors. All right, folks. So that is where your next notes will pick back up at. And we will see you next time. I hope you're hanging in there and following along with these videos. But, again, you know where to get a hold of me, and we'll be done hopefully rather shortly here. There's not much left to present. Dot products and cross products will happen really quickly, and then we finish up with just looking at some curves and surfaces that are going to be what we come back to in Calc 3 in terms of how we want to understand some of these ideas in 3-dimensional space. So, with that said, folks, I will stop there. I hope you're all doing well. See you next time.